Voyager 1 is traveling at 38,000 miles per hour, fast enough to circle Earth in 40 minutes. It's been racing through space since 1977, covering over 15 billion miles, and after all that time, all that distance, all that incredible speed, and it still hasn't left the solar system. To understand how long it takes to leave the solar system, we first need to figure out where our solar system actually ends. This might sound simple, but it's one of those questions that gets more complicated the deeper you dig. Is the edge where the sun's light fades, where its gravity no longer dominates, where the solar wind stops blowing? Each definition gives us a dramatically different answer, and each reveals something profound about our place in the cosmos. Let's start with what most people think of as the solar system, the realm of the planets. Neptune, our outermost major planet, orbits about 3 billion miles from the Sun. That's 30 times farther than Earth. If you could travel at the speed of a commercial jet, about 500 miles per hour, it would take you nearly 700 years just to reach Neptune. But Neptune isn't even close to the edge of our solar system. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies including Pluto and countless other frozen worlds. This region extends from about 3 billion to 5 billion miles from the Sun. The New Horizons spacecraft, one of the fastest human-made objects ever launched, took 9.5 years to reach Pluto, traveling at speeds up to 36,000 miles per hour. And Pluto is just the beginning of the outer territories. Scientists often define the edge of the solar system as the Heliopause, the boundary where the solar wind, that stream of charged particles flowing from our Sun, finally gives way to the interstellar medium. This is where Voyager 1 made history. On August 25, 2012, after 35 years of travel, and at a distance of about 11 billion miles from the Sun, Voyager 1 crossed the Heliopause and entered interstellar space. The moment was detected by Voyager's instruments as a dramatic change in the environment around the spacecraft. The density of charged particles from our Sun dropped to nearly zero, while cosmic rays from interstellar space increased dramatically. It was like stepping out of a warm house into a cosmic winter, except this winter is filled with high-energy particles from distant supernovae and other galactic phenomena. But here's where things get philosophically interesting. While Voyager 1 has left the Sun's magnetic bubble, it hasn't escaped the Sun's gravitational influence, not even close. The Sun's gravity extends far, far beyond the Heliopause, holding on to a vast sphere of comets and icy bodies called the Oort cloud. This cosmic snow globe might extend as far as 2 light-years from the Sun, nearly halfway to the nearest star. The Oort cloud represents the true gravitational boundary of our solar system. It's a spherical shell of trillions of comets, so distant and dark that we've never directly observed it. We only know it exists because long-period comets that visit the inner solar system must come from somewhere, and their orbits point back to this distant reservoir. If you want to truly leave the solar system, you need to escape the Sun's gravitational grip entirely, which means passing beyond the Oort cloud. At Voyager 1's current speed of about 38,000 miles per hour, it will take roughly 300 years to reach the inner edge of the Oort cloud. But the Oort cloud itself is vast, possibly extending from about 2,000 astronomical units to 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. This means the outer edge of the Oort cloud could be nearly 100,000 times farther from the Sun than Earth is. Hey, if this cosmic journey is already stretching your imagination, make sure to subscribe and drop a like on this video. We're just scratching the surface of understanding the true scale of our solar system and what it really means to leave it behind. To cross the entire Oort cloud and truly exit the solar system, Voyager 1 will need about 30,000 years. Think about that, 30,000 years. When Voyager launched, humans were still arguing about whether personal computers would ever be useful. In 30,000 years, who knows what humanity might become if we're still around at all? Yet this little spacecraft, carrying a golden record with sounds and images from Earth, will still be sailing through the outer reaches of our solar system. The Voyager missions give us our best real-world data on leaving the solar system, but they're not our only ambassadors to the stars. Pioneer 10 and Pioneer 11, launched in the early 1970s, are also heading out of the solar system, though their power sources have long since failed and we've lost contact with them. New Horizons, after its spectacular flyby of Pluto in 2015, is also on an escape trajectory and will eventually leave the solar system. But these spacecraft are crawling compared to what's theoretically possible. They're using conventional chemical rockets with gravitational assists from planets, essentially the same technology we've been using since the beginning of the space age. If we want to leave the solar system faster, we need to think bigger, bolder, and perhaps a bit crazy. Project Orion, conceived in the 1950s, proposed using nuclear explosions to propel a spacecraft. By detonating small nuclear bombs behind a massive pusher plate, engineers calculated they could achieve speeds of 3 to 5% the speed of light. At those speeds, you could reach the Heliopause in just a few months and clear the Oort cloud in a few hundred years instead of tens of thousands. Of course, the slight problem of launching hundreds of nuclear weapons into space made this politically and environmentally impossible. More recently, the breakthrough Starshot project has proposed using powerful lasers to accelerate tiny spacecraft to 20% the speed of light. These star chips, weighing just grams, would be attached to light sails that catch laser beams from Earth. In theory, they could reach the nearest star in just 20 years, but could they leave our solar system? At 20% light speed, they'd reach the Heliopause in about 3 days, clear the entire Oort cloud in just 30 years. But here's the reality check. These advanced propulsion concepts remain largely theoretical. The engineering challenges are staggering. Breakthrough Starshot's laser array would need to be about a square kilometer in size, perfectly synchronized, and capable of focusing enormous power on a target just meters across as it accelerates away at incredible speeds. We're probably decades away from even attempting such technology. So what can we actually achieve with current technology? Well, this brings up a fascinating question that I explored in detail in my video about how fast we can travel in space right now. The answers might surprise you. Our fastest spacecraft use a combination of powerful rockets and clever gravity assists, stealing energy from planets to slingshot themselves to higher speeds. But even our best efforts pale in comparison to the distances we're talking about. The link is in the description and pinned on the comments. The Parker Solar Probe, launched in 2018, will become the fastest human-made object in history as it dives close to the Sun, reaching speeds of 430,000 miles per hour by 2024. That's about 200 miles per second, fast enough to travel from New York to Los Angeles in about 12 seconds. Yet, even at this incredible speed, it would still take over 2,500 years to reach the Oort cloud's outer edge. This highlights a fundamental challenge of interstellar travel. Space is mind-bogglingly big. We often use light years to measure cosmic distances because anything else becomes unwieldy. Light travels at 186,000 miles per second, the ultimate speed limit of the universe. A light year is the distance light travels in 1 year, about 6 trillion miles. The outer edge of the Oort cloud at nearly 2 light years means that even light itself takes 2 years to travel that distance. But leaving the solar system isn't just about distance and speed, it's about energy. Every object in the solar system is trapped in the sun's gravitational well. Imagine the sun sitting at the bottom of an enormous bowl with all the planets, asteroids, and comets rolling around the sides, To leave the solar system, you need enough energy to climb up and out of that bowl entirely. The escape velocity from Earth's surface is about 25,000 miles per hour, but that just gets you away from Earth. To escape the solar system entirely from Earth's orbit, you need to be traveling at about 94,000 miles per hour relative to the Sun. This is why spacecraft like Voyager needed gravitational assists from giant planets. Jupiter's enormous gravity gave Voyager the extra kick it needed to reach solar escape velocity. Speaking of Voyager, let's talk about what it's actually experiencing out there in interstellar space. The environment beyond the heliopause is alien in ways that challenge our earthbound intuitions. The temperature is about -450 degrees Fahrenheit, just a few degrees above absolute zero. The density of matter is so low that Voyager encounters only about 1 atom per cubic inch, compared to about 30 quintillion atoms per cubic inch in Earth's atmosphere. Yet this seeming emptiness is full of activity. Cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events, constantly bombard the spacecraft. The magnetic field of the galaxy itself creates a subtle but measurable influence. And occasionally, Voyager detects mysterious phenomena that scientists are still trying to understand, like the persistent hum of plasma waves in interstellar space discovered in 2021. The power systems on Voyager are gradually failing. The spacecraft uses radioisotope thermoelectric generators, essentially nuclear batteries that convert the heat from decaying plutonium into electricity. When launched, these generators produced about 470 watts of power. Today, they produce less than half that, and by 2025, Voyager will need to shut down its last scientific instrument to conserve power for communication with Earth. This raises a poignant question: when does a mission to leave the solar system truly end? When the spacecraft crosses the heliopause, when it clears the Oort cloud, when we lose contact with it? Or does it continue as long as the spacecraft exists, carrying its golden record through the cosmos like a message in a bottle thrown into an infinite ocean? The golden records on Voyager 1 and 2 are perhaps humanity's most ambitious attempt at communication. They contain sounds and images from Earth, greetings in 55 languages, music from different cultures, sounds of nature, and scientific diagrams. The records are designed to last billions of years in the interstellar environment. Long after humanity has vanished, long after our sun has died, these records will still be sailing through the galaxy, carrying the essence of what we were. But let's zoom back to the present and talk about the immediate future of leaving the solar system. NASA and other space agencies are developing new technologies that could dramatically reduce travel times. Solar sails use the pressure of sunlight itself for propulsion, slowly but steadily accelerating spacecraft without using any fuel. Ion drives, already used on missions like Dawn and Hayabusa, achieve much higher exhaust velocities than chemical rockets, though with very low thrust. The most promising near-term technology might be solar gravity assists. By diving close to the Sun and using its enormous gravity, spacecraft can achieve incredible speeds. The proposed Interstellar probe mission would use this technique to reach speeds of over 200,000 miles per hour, allowing it to travel 500 astronomical units in just 15 years, fast enough to study the outer reaches of our solar system within a human lifetime. But even these advanced missions would take centuries or millennia to fully escape the Sun's gravitational influence. This brings us to a profound realization. Leaving the solar system is not a journey measured in human lifetimes, but in the lifetimes of civilizations. The spacecraft we launch today are emissaries not just from our generation, but from our entire species to the cosmos. Think about the audacity of that. We're sending messages that won't reach their destination for tens of thousands of years. We're launching missions that will outlive not just us, but potentially our entire civilization. The Voyager spacecraft will still be traveling through interstellar space when the pyramids have crumbled to dust, when new ice ages have come and gone, when the very continents have shifted positions. This perspective transforms the question, how long does it take to leave the solar system, into something much deeper. It's not just about velocity and distance, it's about our relationship with time itself. We're a species that typically thinks in days, years, maybe decades. But space exploration forces us to think in centuries, millennia, even millions of years. The Oort cloud, that vast sphere of comets marking the true edge of our solar system, will still be there when our sun begins to die in about 5 billion years. Any spacecraft we launch today will witness the death of our star from the outside, having long ago escaped to become eternal wanderers in the galaxy. They'll carry with them the only evidence that we ever existed, the only proof that on one small world orbiting an ordinary star, matter organized itself into patterns complex enough to wonder about the universe and brave enough to explore it. Let's put this journey in perspective with some numbers that will absolutely melt your brain. If we shrink the solar system down to a scale where Earth is the size of a marble, about 1 centimeter across, the Sun would be a beach ball about 1 meter wide, sitting about 117 meters away. Neptune would be another marble, about 3.5 kilometers from the Sun. But the Heliopause, where Voyager crossed into interstellar space, would be about 14 kilometers away. And the outer edge of the Oort cloud? That would be 156 kilometers from our beach ball Sun. On this scale, Voyager 1, traveling at its current speed, would be crawling along at about 4 millimeters per hour. It would take nearly 4.5 years just to travel 1 kilometer. To reach the outer edge of our scaled-down Oort cloud would take about 700 years. And remember, this is with the solar system shrunk down to fit inside a small country. The real thing is so vast that our minds simply can't process it. This cosmic scale has profound implications for how we understand our missions to leave the solar system. When we talk about exploring space, we're really just dipping our toes in our own cosmic backyard. Every human who has ever lived, every civilization that has risen and fallen, every triumph and tragedy of our species, all of it has happened within the gravitational embrace of one ordinary star among hundreds of billions in our galaxy. The spacecraft leaving our solar system carry more than scientific instruments. They carry the dreams and aspirations of the only species we know of that looks up at the stars and wonders what's out there. The Pioneer plaques, designed by Carl Sagan and others, show a man and woman, a map of our solar system, and our location in the galaxy. They're like cosmic postcards saying we were here, we existed, we wondered. But these messages face a lonely journey. Space between stars is emptier than the best vacuum we can create on Earth. In interstellar space, you might find 1 atom per cubic centimeter, and most of that is hydrogen, the simplest element. For comparison, a cubic centimeter of the air you're breathing right now contains about 30 quintillion atoms. The loneliness of interstellar space is absolute in a way that's difficult to comprehend. Yet this emptiness is not sterile. As our spacecraft have discovered, interstellar space hums with activity. Cosmic rays zip through at nearly the speed of light. Magnetic fields from distant stars create a complex, ever-changing tapestry. Dust grains, smaller than smoke particles but traveling at tens of thousands of miles per hour, occasionally impact our spacecraft. Each grain is a tiny piece of some distant star that died millions or billions of years ago. The Voyager spacecraft have revolutionized our understanding of the boundary between our solar system and interstellar space. Before Voyager, scientists debated whether the transition would be gradual or sudden. Voyager 1's crossing answered that question. It's surprisingly sharp. Over the course of just a few months in 2012, Voyager saw the density of solar particles drop by a factor of more than 1,000, while cosmic rays increased by a similar amount. But Voyager also discovered something unexpected. The heliopause isn't a simple bubble. It's a complex, dynamic boundary shaped by the interaction between the solar wind and the interstellar medium. Imagine two rivers meeting. There's turbulence, eddies, and mixing. The boundary of our solar system is similar, but the rivers are made of charged particles and magnetic fields moving at millions of miles per hour. The Interstellar Boundary Explorer, or IBEX, launched in 2008, has been mapping this boundary from Earth orbit. It discovered a mysterious ribbon of energetic, neutral atoms that scientists are still trying to understand. This ribbon might be caused by the interaction between our solar system and the magnetic field of the local interstellar cloud we're passing through. Yes, our entire solar system is moving through space, orbiting the center of the Milky Way at about 515,000 miles per hour. This motion adds another layer of complexity to leaving the solar system. Not only are our spacecraft moving away from the Sun, but the Sun itself is carrying the entire solar system through space. We're like passengers on a cosmic train, and our spacecraft are jumping off while the train keeps moving. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445, not because Voyager is aimed at it, but because that star and our Sun are moving relative to each other. The implications are staggering. The spacecraft we send out of our solar system aren't just leaving home, they're becoming independent actors in the galactic dance. They'll orbit the center of the Milky Way just like stars do, taking about 230 million years to complete each circuit. By the time Voyager completes its first full orbit of the galaxy, Earth will be unrecognizable, humanity will likely be extinct or transformed beyond recognition, and our Sun will be noticeably older and brighter. Yet the spacecraft will endure. In the vacuum of interstellar space, with no air to cause corrosion and no weathering, the Voyager spacecraft could remain recognizable for millions of years. The golden records, made of gold-plated copper and encased in aluminum, could last even longer, potentially billions of years. They're among the longest-lasting artifacts humanity has ever created. This durability raises fascinating questions about the ultimate fate of our interstellar ambassadors. Long after they've stopped transmitting, long after humanity has forgotten them, they'll continue their journey. They might be found by alien civilizations we can't imagine. They might fall into distant star systems billions of years from now, or they might wander the galaxy forever, eternal monuments to a species that once dreamed of touching the stars. The physics of leaving the solar system also teaches us about the nature of gravity itself. Newton showed us that gravity's reach is infinite. Technically, every atom in the universe exerts a gravitational pull on every other atom, but gravity weakens with distance according to the inverse square law. Double the distance and gravity becomes 4 times weaker. At the distance of the Oort cloud, the Sun's gravity is incredibly feeble, but it's still enough to hold on to those distant comets. This is why defining the edge of the solar system is so tricky. If we define it as where the Sun's gravity stops having any effect, then our solar system is infinite. If we define it as where the Sun's gravity no longer dominates over the gravity of other stars, then the boundary depends on where the nearest stars are. The Oort cloud represents a practical compromise. It's where objects can orbit the Sun for billions of years without being pulled away by passing stars. The discovery of the Kuiper Belt and the theoretical Oort cloud has completely transformed our picture of the solar system. When I was young, textbooks showed the solar system ending just past Pluto. Now we know that was like saying Earth ends at your front door. The The Kuiper Belt alone is 20 times wider than the region containing all the planets. And the Oort cloud dwarfs even that, extending perhaps 1,000 times farther from the Sun than Neptune. This vast scale forces us to reckon with our cosmic insignificance in a way that's both humbling and inspiring. When NASA's New Horizons flew past Pluto in 2015, it took 4.5 hours for the signal to reach Earth. That was just from Pluto. A signal from Voyager 1 now takes over 22 hours to reach us, traveling at the speed of light. And that's still within what we might generously call our cosmic neighborhood. If an alien civilization at the edge of the Oort cloud tried to communicate with Earth using radio waves, the message would take 2 years to arrive. Our response would take another 2 years to get back. A simple conversation would unfold over generations. This is the reality of cosmic distances. They don't just separate locations in space, they separate moments in time. The time delay in communications with our distant spacecraft creates unique operational challenges. When mission controllers send a command to Voyager, they're essentially sending a message into the past, knowing the spacecraft will receive it nearly a day later. If something goes wrong, if Voyager encounters an unexpected problem, Earth won't know for another 22 hours. The spacecraft must handle any emergency entirely on its own, using 46-year-old computer technology with less processing power than a modern calculator. This isolation will only increase as our spacecraft venture farther into the void. Eventually, the signals will become too weak to detect, and we'll lose contact with our cosmic ambassadors forever. NASA estimates that we'll lose communication with Voyager 1 around 2025, not because the spacecraft will stop transmitting, but because its power will drop below the threshold needed to send a detectable signal across the vast gulf of space. The moment we lose contact with Voyager will be profoundly poignant. It will mark the end of humanity's first interstellar mission, at least from our perspective. But for Voyager, the journey will have barely begun. It will continue sailing through the darkness, carrying its golden record and the faint traces of human ambition, long after the last radio wave has faded into cosmic static. Let's talk about what our spacecraft are actually finding as they leave the solar system. The boundary regions have proven to be far more complex and dynamic than anyone expected. Voyager discovered that the Heliopause, that boundary where the solar wind meets interstellar space, actually moves. It breathes in and out with the 11-year solar cycle, expanding when the Sun is active and contracting when it's quiet. Even more surprisingly, Voyager found that the magnetic field direction changes dramatically at the Heliopause. Inside our solar system, the magnetic field is oriented east-west, carried by the solar wind. Outside, in interstellar space, it runs roughly north-south, following the magnetic field of our local galactic neighborhood. It's like stepping from one room to another and finding that gravity points in a different direction. The temperature also changes in unexpected ways. Scientists expected interstellar space to be slightly warmer than the outer solar system because of heating from distant stars. Instead, Voyager found it's about the same temperature, nearly absolute zero. But the way heat moves is completely different. In interstellar space, there are so few particles that conventional heat transfer basically stops. A hot object stays hot, and a cold object stays cold for extraordinary lengths of time. These discoveries are rewriting textbooks and forcing scientists to revise their models of how stars interact with their galactic environment. Our Sun, it turns out, creates a much larger and more complex bubble in space than we thought. This bubble, called the heliosphere, might be shaped less like a sphere and more like a comet, with a long tail streaming behind us as we move through the galaxy. The Interstellar Mapping and Acceleration Probe, or IMAP, scheduled for launch in 2025, will study this boundary in unprecedented detail. It will help us understand not just the edge of our solar system, but how all star systems interact with the interstellar medium. This knowledge is crucial for understanding how cosmic rays are filtered, how stellar neighborhoods evolve, and even how life-friendly conditions are maintained on planets like Earth. But perhaps the most profound discovery from our interstellar missions is philosophical rather than scientific. These spacecraft have given us our first true perspective on our place in the universe. The famous pale blue dot photograph taken by Voyager 1 in 1990 as it looked back at Earth from beyond Neptune shows our planet as a tiny speck in a sunbeam. Every human who has ever lived, every civilization that has risen and fallen, every triumph and tragedy, all of it happened on that barely visible dot. Carl Sagan's reflection on this image remains one of the most moving passages in science communication. He reminded us that Earth is the only home we've ever known, suspended in a sunbeam, a mote of dust in the cosmic dark. The spacecraft leaving our solar system carry this perspective with them. They're not just scientific instruments, they're philosophical instruments, teaching us about our true cosmic context. The future of leaving the solar system looks both promising and challenging. NASA is studying an interstellar probe mission that would be specifically designed to explore the outer heliosphere and nearby interstellar space. Using a close pass of the Sun for a gravitational boost, it could reach speeds of over 200,000 miles per hour, about 6 times faster than Voyager. Even more ambitious is the breakthrough Starshot project I mentioned earlier. By using powerful lasers to push tiny spacecraft with light sails, we might achieve speeds of 20% the speed of light. At those velocities, reaching the Heliopause would take just days, and clearing the Oort cloud would take decades instead of millennia. But the technical challenges are staggering, and we're probably decades away from even attempting such a mission. The Chinese National Space Administration has proposed their own interstellar mission, Interstellar Express, which would use nuclear electric propulsion to reach 200 astronomical units in just 25 years. The European Space Agency is considering similar missions. It seems that leaving the solar system has become not just a scientific goal, but a milestone for spacefaring civilizations. But why does leaving the solar system matter so much to us? Part of it is simply human nature. We're explorers, always wanting to see what's over the next horizon. But it's also about survival. Our sun won't last forever. In about 5 billion years, it will expand into a red giant, probably engulfing Earth. Long before that, in just 1 billion years, the sun will have grown bright enough to boil away Earth's oceans. Learning to leave the solar system isn't just about satisfying curiosity, it's about developing the technologies and knowledge our descendants might need to survive. Every spacecraft we send beyond the Heliopause is a small step toward ensuring that life from Earth could potentially outlive our planet and even our star. There's also the search for life. While our current interstellar missions aren't designed to search for alien civilizations, they're proving that interstellar travel is possible, at least for robotic spacecraft. If we can send probes to other stars, then other civilizations could do the same. Every spacecraft leaving our solar system is both an ambassador and a scout, representing humanity while exploring the cosmic ocean that surrounds our stellar island. The search for life brings us to one of the most tantalizing aspects of leaving the solar system. What's actually out there in interstellar space? We used to think it was empty, just a vast void between stars. But our spacecraft have revealed that interstellar space is surprisingly rich and complex. There are magnetic fields, cosmic rays, interstellar dust, and even complex organic molecules floating in the darkness. In 2019, astronomers detected the first confirmed interstellar object passing through our solar system, Oumuamua, a strange, elongated object that sparked intense debate about its nature. Some scientists even suggested it might be artificial, though most believe it's a natural object, perhaps a shard of a planet destroyed in some distant star system. Then, in 2019, we spotted a second interstellar visitor, the comet Borisov, which looked more like comets from our own solar system, but with subtle differences in its composition. These interstellar visitors remind us that space between stars isn't empty. It's a highway where objects from different star systems can meet and mingle. Our spacecraft leaving the solar system will eventually become interstellar objects themselves, perhaps passing through alien solar systems billions of years from now. It's a form of cosmic cross-pollination that happens on timescales beyond human comprehension. The chemistry of interstellar space is fascinatingly complex. Radio telescopes have detected over 200 different molecules in interstellar clouds, including organic compounds like methanol, formaldehyde, and even amino acids, the building blocks of life. These molecules form on the surfaces of tiny dust grains in the cold of space, creating a kind of cosmic chemistry set that might seed planets with the ingredients for life. Our departing spacecraft are sampling this interstellar medium directly for the first time. Voyager's instruments have detected subtle changes in the cosmic ray spectrum that tell us about supernova explosions that happened millions of years ago and thousands of light years away. Each particle hitting Voyager's detectors is a messenger from distant cosmic events carrying information across the galaxy at nearly the speed of light. The magnetic fields in interstellar space are particularly intriguing. They're about 100,000 times weaker than Earth's magnetic field, but they extend across vast distances and play a crucial role in shaping the galaxy. These fields guide cosmic rays, influence star formation, and might even affect the development of life on planets. Voyager's magnetometer is giving us our first direct measurements of these fields, revealing a magnetic landscape more complex than anyone expected. But let's zoom out even further and consider what leaving the solar system means for the future of humanity. Every great journey begins with a single step, and our current missions are those first tentative steps into the galactic ocean. They're proving that it's possible to build machines that can survive the journey between stars, even if that journey takes tens of thousands of years. This has profound implications for the long-term survival of life from Earth. Even if we never develop faster-than-light travel, even if we're limited to the speeds we can achieve today, it's still possible to spread life throughout the galaxy. It would take millions of years, but that's a blink of an eye in cosmic terms. A civilization that could build self-replicating probes could colonize the entire galaxy in just a few million years, even traveling at speeds we can achieve today. This realization leads to one of the great mysteries in astronomy, the Fermi paradox. If it's possible to colonize the galaxy in a few million years, and the galaxy is billions of years old, then where is everybody? Why haven't we detected any signs of alien civilizations? One possibility is that leaving a solar system is much harder than we think, that there are challenges we haven't yet discovered that make interstellar travel effectively impossible. Or perhaps life is incredibly rare, and we're among the first civilizations in our galaxy to develop technology. Or maybe civilizations tend to destroy themselves before they can spread to the stars. The spacecraft we're sending out of our solar system are, in a sense, testing these possibilities. They're proving that at least robotic interstellar travel is possible, adding one small piece to the vast puzzle of our cosmic solitude. The emotional and philosophical impact of leaving the solar system can't be overstated. For all of human history, we've been bound to one star, trapped in its gravity well like insects in amber. The spacecraft crossing the Heliopause represent our first escape from that trap. They're the first human artifacts to taste true freedom, to become citizens of the galaxy rather than just our solar system. This transition from a single star species to a galactic species, even if only through our robotic proxies, represents a fundamental change in our cosmic status. We're no longer just passive observers of the universe. We're active participants, sending our ambassadors to join the galactic community. It's a coming-of-age moment for our species, like a child taking their first steps outside the family home. The golden records on the Voyager spacecraft embody this transition perfectly. They contain greetings in 55 human languages, but also songs of humpback whales, the sound of rain, and a mother's first words to her newborn child. They carry images of human anatomy, mathematical concepts, and scenes of life on Earth. They're an attempt to compress the essence of a living world onto a 12-inch disc, a message of almost heartbreaking optimism thrown into the cosmic dark. What strikes me most about these records is their faith in the future. The team that created them, led by Carl Sagan, believed that somewhere, somewhen, an intelligence might find these spacecraft and wonder about the beings who sent them. They believed that curiosity and wonder are universal, that any civilization advanced enough to find and retrieve the records would want to know about us. It's a belief in cosmic community that transcends species, planets, and even time itself. The records also represent a kind of immortality. Long after our cities have crumbled, long after our languages are forgotten, long after our species has evolved into something unrecognizable or gone extinct entirely, these golden discs will still be sailing through the galaxy. They're our shot at cosmic permanence, our attempt to leave a mark on the universe that will outlast the stars themselves. But leaving the solar system isn't just about grand philosophical statements, it's also about practical science. The outer regions of our solar system and the boundary with interstellar space are laboratories for understanding fundamental physics. How do magnetic fields behave over vast distances? How do cosmic rays propagate through the galaxy? How do stars and the interstellar medium interact? These questions have implications for everything from the formation of planets to the development of life. The data from Voyager has already revolutionized our understanding of cosmic rays. These high-energy particles, accelerated by supernova explosions and other violent events, constantly bombard Earth. Our atmosphere protects us from most of them, but they can affect everything from cloud formation to DNA mutations. Understanding cosmic rays is crucial for predicting space weather, protecting astronauts, and even understanding evolution on Earth. The journey to leave our solar system has also taught us humility about the sheer scale of space and time. When Voyager 1 launched in 1977, Jimmy Carter was president, Star Wars had just premiered in theaters, and the internet didn't exist. Now, 46 years later, Voyager has traveled over 15 billion miles, and it's still just barely outside our front door in cosmic terms. If the Milky Way galaxy were the size of the United States, Voyager would have traveled about the width of a human hair. This perspective shift is perhaps the greatest gift of our interstellar missions. They force us to think beyond human timescales, beyond national boundaries, beyond the concerns that dominate our daily lives. When you're planning a mission that won't reach its destination for 30,000 years, you can't help but think about the long-term future of humanity and our planet. The technology we've developed to send spacecraft out of the solar system has already transformed life on Earth. The miniaturized electronics needed for deep space missions led to advances in computers and smartphones. The need for reliable long-distance communication drove innovations in error-correcting codes that now power the Internet. The precision navigation required for interplanetary travel improved GPS technology. Every time you use your phone's map app, you're benefiting from technologies developed to help us leave the solar system. But perhaps more important than the technological spin-offs are the conceptual breakthroughs, learning to think in astronomical units and light years, to plan missions lasting decades, to build machines that must work perfectly with no possibility of repair. These challenges have expanded human capability in ways that go beyond any specific technology. We've learned to be more patient, more precise, and more ambitious in our thinking. The international cooperation required for tracking and communicating with distant spacecraft has also brought humanity together in subtle but important ways. The Deep Space Network, with giant radio dishes in California, Spain, and Australia, ensures continuous contact with our interstellar ambassadors as Earth rotates. Scientists from different nations collaborate on analyzing the data, sharing insights that belong to all humanity rather than any single country. This spirit of international cooperation in space exploration offers hope for our species. If we can work together to send spacecraft to the stars, perhaps we can work together to solve the challenges facing our planet. The perspective gained from leaving the solar system, seeing Earth as a tiny, fragile oasis in the cosmic dark, might be exactly what we need to become better stewards of our homeworld. Let's talk about the future missions being planned to explore the boundary of our solar system. The interstellar probe concept being studied by Johns Hopkins Applied Physics Laboratory would be specifically designed to explore the outer heliosphere and nearby interstellar space. Using a close flyby of the Sun to gain speed, a maneuver called an Oort maneuver, it could reach velocities of over 200,000 miles per hour. This probe would carry instruments specifically designed to study the interstellar medium, including dust detectors, magnetometers, and particle analyzers, far more sensitive than Voyager's aging instruments. It could reach the Heliopause in just 15 years and continue operating for 50 years or more, giving us our first detailed look at our cosmic neighborhood. China's proposed Interstellar Express mission would use nuclear electric propulsion, ion engines powered by a nuclear reactor, to achieve even higher speeds. This technology, while complex and expensive, could enable spacecraft to reach hundreds of astronomical units in just decades rather than centuries. The European Space Agency is considering similar missions, recognizing that understanding our place in the galaxy requires actually going there. But the most ambitious proposals involve breakthrough propulsion technologies that could dramatically reduce travel times. Fusion rockets, if we can ever make them work, could potentially achieve speeds of 3 to 5% the speed of light. At those velocities, reaching the Heliopause would take just months, and clearing the Oort cloud would take centuries rather than tens of millennia. Even more exotic proposals include antimatter propulsion, where the annihilation of matter and antimatter would provide the ultimate energy source. A few grams of antimatter could propel a spacecraft to significant fractions of light speed. Of course, we currently produce antimatter in quantities measured in individual atoms, and storing it safely is an unsolved challenge. But the physics is sound, it's just an engineering problem, albeit one that might take centuries to solve. The Breakthrough Starshot project represents a completely different approach. Instead of trying to accelerate large spacecraft to high speeds, it would send swarms of tiny probes, each weighing just grams. These starchips would be attached to light sails a few meters across, pushed by powerful laser beams from Earth. The physics works out. You could accelerate these tiny probes to 20% light speed, reaching the nearest stars in just 20 years. Of course, the challenges are immense. The laser array would need to be about a square kilometer in size, perfectly synchronized, and capable of focusing terawatts of power on targets just meters across. The probes would need to survive acceleration of tens of thousands of Gs, navigate autonomously to their targets, and somehow transmit data back across light years of space. But unlike fusion or antimatter rockets, this technology requires no new physics, just extraordinary engineering. These future missions raise profound questions about the nature of exploration itself. If we send tiny robotic probes to other stars at 20% light speed, but they can't slow down and can only transmit brief snapshots as they fly past, is that really exploration? Or is true exploration something that requires human presence, the ability to stop, investigate, and understand? Different cultures and individuals will answer these questions differently. For some, the mere act of sending human artifacts to other stars is profoundly meaningful, regardless of what data they return. For others, exploration requires human eyes and human understanding. The spacecraft leaving our solar system today represent just the beginning of this debate, a debate that will likely continue for centuries as our capabilities expand. The philosophical implications extend even further when we consider generation ships or embryo ships that could actually transport human life to other stars. These missions would take centuries or millennia, requiring either multiple generations living and dying in space or frozen embryos to be raised by AI systems upon arrival. The ethical questions are staggering. Do we have the right to commit unborn generations to life in space? Can human culture and knowledge be preserved across such vast timescales? These questions become even more complex when we consider that by the time a generation ship reached another star, technology on Earth would have advanced dramatically. A ship launched today at 1% light speed would take 400 years to reach Proxima Centauri. But in 400 years, we might develop technology that could make the journey in 40 years. The original colonists would arrive to find their descendants had beaten them there, a cosmic version of the tortoise and hare. This weight calculation suggests that there might be an optimal time to launch interstellar missions, not too early, when technology is primitive, but not too late, when all the good planets are taken. Of course, this assumes continued technological progress, which is far from guaranteed. Civilizations can stagnate, decline, or destroy themselves. The spacecraft leaving our solar system today might be the high watermark of human achievement, our greatest accomplishment before some catastrophe ends our cosmic ambitions. This sobering possibility adds urgency to our interstellar missions. Every spacecraft we send beyond the Heliopause is a backup copy of human achievement, a message to the universe that we existed and dreamed of the stars. Even if humanity disappears tomorrow, Voyager will continue its journey for millions of years, carrying evidence of what we were capable of at our best. The cultural impact of leaving the solar system extends far beyond science and technology. Artists, writers, and musicians have been inspired by our interstellar missions. The Golden Record itself is a work of art, carefully curated to represent the diversity and beauty of life on Earth. Science fiction authors have imagined countless scenarios for interstellar travel, from generation ships to warp drives, each exploring different aspects of what it means to leave our cosmic home. These cultural works aren't just entertainment, they're part of how we process the enormous implications of becoming an interstellar species. They help us imagine futures we can't yet build, explore ethical dilemmas we haven't yet faced, and prepare psychologically for a universe vastly larger than our everyday experience. In a sense, we're leaving the solar system in our imaginations long before our bodies can follow. The spiritual and religious implications are equally profound. Many faith traditions have had to grapple with what it means to be human in a universe of billions of galaxies. If life exists elsewhere, does it have souls? If we spread life to other worlds, are we fulfilling a cosmic purpose or committing cosmic vandalism? These questions don't have easy answers, but they're part of the human conversation sparked by our first steps into interstellar space. Some see leaving the solar system as humanity's destiny, written in our DNA by billions of years of evolution. Life has always expanded to fill available niches, from the ocean to land, from the ground to the air. Spreading beyond Earth, beyond the solar system, to the stars themselves might be the natural continuation of this ancient pattern. We might be the universe's way of spreading life and consciousness throughout the galaxy. Others argue that leaving the solar system represents a dangerous hubris, an attempt to escape the limits that define us. They point out that we haven't even learned to live sustainably on Earth. What makes us think we can terraform other worlds or build generation ships? Perhaps wisdom lies in accepting our cosmic boundaries, in learning to thrive within the solar system nature gave us rather than always seeking new frontiers. Both perspectives have merit, and the tension between them drives much of our space exploration efforts. We reach for the stars while still struggling to understand our own planet. We send messages to hypothetical aliens while still learning to communicate with each other. We dream of cosmic immortality while individual human lives remain frustratingly brief. These contradictions aren't flaws, they're what make us human. The practical challenges of maintaining communication with spacecraft leaving the solar system reveal the delicate thread connecting us to our cosmic ambassadors. The Deep Space Network's 70-meter dishes can detect signals weaker than a billionth of a watt, like trying to see a 20-watt light bulb from 10 billion miles away. But even these magnificent instruments have limits. As our spacecraft venture farther into the void, their signals grow ever fainter. Engineers have developed ingenious techniques to extend communication range. They use error-correcting codes that can reconstruct messages even when most of the signal is lost in noise. They coordinate multiple dishes to act as a single, giant antenna. They've even learned to use the spacecraft's motion relative to Earth to compress data into stronger signals. But ultimately, physics imposes hard limits. The inverse square law means that doubling the distance requires 4 times the power to maintain the same signal strength. This is why we'll eventually lose contact with Voyager, not because the spacecraft fails, but because we can no longer hear its whispers across the cosmic gulf. It's a poignant reminder that exploration has costs, that reaching for the stars means accepting separation and loss. Every mission that leaves the solar system is ultimately a one-way journey, not just for the spacecraft, but for the emotional connection between humanity and our mechanical ambassadors. Yet we continue to launch these missions driven by something deeper than practical considerations. Maybe it's the same impulse that led our ancestors to cross oceans without knowing what lay beyond the horizon. Maybe it's an evolutionary drive to spread and explore that we can't fully articulate. Or maybe it's simply that the universe is there, vast and mysterious, and we can't help but wonder what lies beyond the next boundary. The data returned by spacecraft leaving the solar system has practical applications we're only beginning to understand. Measurements of the interstellar magnetic field help us understand how cosmic rays propagate, which affects everything from satellite operations to airline radiation exposure. Studies of the Heliopause improve our models of how stars interact with their environment, crucial for understanding potentially habitable exoplanets. Even the engineering challenges of these missions drive innovation. Building spacecraft that can operate for decades without maintenance has led to advances in reliability engineering that benefit everything from medical devices to power grids. Learning to communicate across billions of miles has improved our ability to extract signals from noise, benefiting radio astronomy and even cell phone technology. But perhaps the most valuable return from our interstellar missions isn't scientific data or technological advancement, it's perspective. Every image sent back by our distant spacecraft, every measurement of the interstellar medium, every discovery about the boundary of our solar system helps us understand our true place in the cosmos. We're learning that we live in a bubble of warmth and light surrounded by a vast, cold darkness, and that makes our home all the more precious. This cosmic perspective has practical implications for how we manage our planet. Understanding that Earth is a tiny oasis in an unimaginably vast desert makes environmental protection not just important, but essential for survival. Seeing the heliopause, that final boundary between our solar system and interstellar space, reminds us that there's no backup Earth waiting beyond. This is it. This small blue marble is all we have. The search for exoplanets has reinforced this message. We've discovered over 5,000 planets orbiting other stars, but none quite like Earth. Some are too hot, others too cold. Some are gas giants with no solid surface. Others are rocky worlds with no atmosphere. Even the most Earth-like planets we've found have significant differences that would make human life difficult or impossible. The more we explore, the more we realize how special and rare our home truly is. This doesn't mean we should stop reaching for the stars, quite the opposite. Understanding our cosmic context makes exploration even more important. We need to know what's out there, what's possible, what threats might exist, and what opportunities await. But we should explore with humility, recognizing that we carry the only known life in the universe with us wherever we go. The timeline for leaving the solar system also teaches us patience, a virtue often lacking in our instant gratification culture. When we launch a mission to study the outer solar system, we're making an investment that won't pay off for decades. The scientists who design these missions often retire or die before the spacecraft reach their destinations. It's the ultimate act of faith in the future, a gift from one generation to the next. This intergenerational aspect of space exploration creates unique challenges and opportunities. How do you maintain institutional knowledge across decades? How do you ensure that someone will still be listening when a spacecraft finally reaches its target? NASA has had to develop special programs to train young engineers on old technology, ensuring that expertise in 1970s-era electronics doesn't disappear before Voyager falls silent. The longevity of these missions also creates unexpected connections across time. Scientists analyzing Voyager data today might not have been born when the spacecraft launched. They're collaborating across decades with colleagues they've never met, united by a shared mission to push the boundaries of human knowledge. It's a kind of time travel where past and present work together to explore the future. The economic arguments for leaving the solar system are complex and often contentious. These missions cost billions of dollars and return no immediate economic benefit. Critics argue that the money would be better spent on Earth, addressing poverty, disease, and environmental destruction. It's a fair point. The cost of a single interstellar mission could fund thousands of schools or hospitals, but supporters counter that the benefits, while indirect, are real and lasting. The technologies developed for space exploration have generated economic returns many times their initial investment. The inspiration provided by these missions encourages young people to pursue careers in science and engineering, driving innovation that benefits everyone. And the knowledge gained helps us understand and protect our own planet. There's also the insurance argument. Spreading life beyond Earth, beyond the solar system, is the ultimate backup plan for our species and our biosphere. Asteroids, supervolcanoes, nuclear war, climate change, or eventual solar evolution, any of these could end life on Earth. But if we've spread to other star systems, life itself becomes much harder to extinguish. The spacecraft leaving our solar system today are tiny first steps toward that cosmic insurance policy. The philosophical implications of becoming a multi-stellar species are staggering. Would humans living around other stars still be human? How would cultures evolve in isolation across light years? Would we fragment into separate species, each adapted to their local conditions? Or would we maintain unity through some form of communication, even if conversations take years or decades? These questions might seem premature when our fastest spacecraft will take 30,000 years just to leave the solar system. But the decisions we make today about how to explore space will shape the trajectory of life for millions of years to come. The messages we put on our spacecraft, the technologies we develop, the values we embed in our missions, All of these are votes for a particular vision of humanity's future. The Voyager Golden Records represent one vision: peaceful, curious, eager to communicate. They present humanity at its best, omitting our wars, our environmental destruction, our capacity for cruelty. Some have criticized this as dishonest, arguing we should present ourselves as we truly are. Others see it as aspirational, showing not what we are, but what we hope to become. Future missions will face similar choices. Should we send information about our location, potentially inviting contact from alien civilizations? Should we include genetic information that could be used to recreate Earth life? Should we send cultural artifacts, scientific knowledge, or something else entirely? These decisions require us to think carefully about what we value and what legacy we want to leave. The possibility of contact with alien civilizations adds another dimension to leaving the solar system. Every spacecraft we send out is potentially a first contact scenario waiting to happen. The chances might be infinitesimally small, but they're not zero. Somewhere in the galaxy, an alien civilization might detect one of our spacecraft, retrieve it, and decode its messages. What will they think of us? This possibility has led to careful consideration of what we put on our spacecraft. The Pioneer plaques and Voyager records were designed to be as universal as possible, using mathematics and physics that should be the same throughout the universe. But they still embed assumptions about how aliens might perceive and think. Would a truly alien intelligence even recognize our messages as attempts at communication? The SETI Institute and other organizations searching for extraterrestrial intelligence have thought deeply about these questions. They've concluded that mathematics and physics provide the best universal language, but even these might be expressed in ways we can't anticipate. An alien civilization might use completely different sensory modalities. What if they see using radio waves or communicate through magnetic fields? Our golden records might be as incomprehensible to them as their messages would be to us. Yet we keep trying, driven by an optimism that intelligence and curiosity are universal. The very act of sending messages to unknown aliens is an expression of faith in the commonality of conscious experience. We believe that any beings capable of spaceflight will share our wonder at the universe, our desire to communicate, our need to know we're not alone. It's a beautiful assumption, even if we can't prove it's true. The timeline for leaving the solar system also reveals the tension between human lifespans and cosmic scales. A mission that takes 30,000 years to leave the Oort cloud spans roughly 1,000 human generations. That's longer than all of recorded human history. The ancient Sumerians who invented writing are closer to us in time than we are to when Voyager will finally leave the solar system. This temporal gulf creates unique challenges for mission planning. How do you design a message that will still be meaningful after 1,000 generations? Languages evolve, cultures change, entire civilizations rise and fall. The English on the Voyager record might be as incomprehensible to future humans as Linear A is to us today. We're not just communicating across space, but across vast spans of time. Some have proposed that we should launch new missions regularly, each carrying updated messages reflecting humanity's current state. A spacecraft launched today could carry digital libraries with millions of books, images, and videos, far more than Voyager's golden record. Future missions could carry even more, creating a trail of time capsules spreading out from Earth, each capturing a moment in human history. But this raises the question of representation. Who decides what goes on these cosmic messages, whose voices are included, and whose are left out? The Voyager record was created by a small team led by Carl Sagan, and while they tried to be inclusive, it inevitably reflects the perspectives and biases of 1970s America. Future missions will face similar challenges in trying to represent all of humanity. The environmental impact of leaving the solar system is minimal compared to most human activities, but it's not zero. Every rocket launch produces pollution, and the plutonium in radioisotope thermoelectric generators poses risks if a launch fails. As we contemplate more ambitious missions, these impacts will grow. We need to balance our desire to explore with our responsibility to protect the Earth we're exploring from. There's also the question of space debris. While spacecraft leaving the solar system won't contribute to the growing cloud of junk in Earth orbit, they do represent permanent additions to the galaxy's inventory of artificial objects. In billions of years, long after our civilization has vanished, these spacecraft will still be drifting through space. We're leaving a mark on the galaxy that will outlast our species. Some philosophers have argued that we have a responsibility to the universe itself, that consciousness is so rare and precious that we're obligated to spread it as widely as possible. Others contend that we should minimize our cosmic footprint, that the universe was fine for billions of years without us and will be fine long after we're gone. These debates will only intensify as our capabilities for leaving the solar system improve. The psychological impact of knowing we've sent emissaries beyond the solar system is subtle but real. For all of human history, we've been trapped on one world, looking up at the stars but unable to reach them. Now we've broken that barrier, even if only with robotic proxies. We're no longer just earthbound, we're a species that has touched interstellar space. This achievement changes how we see ourselves. We're not just another species competing for resources on a single planet. We're the only known species that has figured out the laws of physics, built machines to explore beyond our world, and sent messages to the stars. That's either a tremendous responsibility or a cosmic accident, depending on your perspective. The future of leaving the solar system depends partly on technological advancement, but mostly on human will. We know how to send spacecraft to the stars, just takes a long time with current technology. The question is whether we'll maintain the vision and commitment needed for such long-term projects. Will future generations continue to fund and support missions launched by their ancestors? Will they still care about spacecraft launched centuries earlier? History provides both encouraging and discouraging examples. Some human projects have been maintained for centuries: cathedrals, universities, scientific observations. Others have been abandoned when priorities shifted or civilizations fell. The spacecraft leaving our solar system represent a bet that humanity will maintain some continuity of purpose across vast spans of time. Climate change adds urgency to these considerations. If we significantly damage Earth's biosphere, will we still have the resources and organization to maintain deep space missions? Will future generations struggling with environmental collapse care about spacecraft heading to the stars? Or will our interstellar ambitions be one more casualty of our failure to live sustainably on Earth? Yet there's also hope that space exploration and environmental protection can reinforce each other. The same technologies that enable interstellar missions, advanced solar panels, nuclear power, closed-loop life support, could help us live more sustainably on Earth. The perspective gained from seeing Earth as a tiny oasis in the cosmic dark motivates environmental protection. And the inspiration from reaching for the stars encourages the kind of long-term thinking we need to solve global problems. The spacecraft leaving our solar system today are just the beginning. They're proof-of-concept missions showing that interstellar travel is possible even with 20th century technology. Future missions will be faster, smarter, and more capable. They'll carry better instruments, more sophisticated messages, and perhaps eventually human colonists. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this one at the left side of the screen. How long would it take to reach each planet in our solar system? In this video, we break down the real travel times to Mercury, Venus, Mars, and the other planets. Using current rocket technology, gravity assists, and even future propulsion concepts like nuclear, ion, and fusion rockets. See you there.